Hey, good morning, everybody. Today's video is about oxidation reduction reactions, sometimes for shorthand referred to as redox reactions. So take a look, please, at this single replacement reaction in which a chunk of solid calcium metal is put in a solution of iron 2 chloride. The reaction occurs, and we end up with calcium chloride in solution and then iron solid at the bottom of the beaker. In this reaction, we have neutral calcium atoms doing the metal thing, which is losing electrons. And as they lose electrons, they become more positive and turn into cations. It's those cations then that form the compound with the anions. So that process of getting more positive, losing electrons to turn into a cation, that's known as an oxidation process. And this little half equation shows what's happening. The calcium atoms are losing electrons and becoming calcium cations. Now that process can't happen without the twin process of reduction. Reduction is where somebody gets more negative. In this example, these iron cations in solution are going to grab those electrons that were given away, and then the cations will turn into neutral iron atoms. That's a process of getting more negative or reduction. That's pretty clear to see because we have metal atoms just blatantly giving away electrons. But sometimes the process is a little more subtle. So let's take a look at this example of two non-metal substances. We have sulfur, non-metal, and we have oxygen gas, non-metal. And when they react together, they form this molecular compound, sulfur dioxide, a gas. This is not ionic. These atoms are covalently bonded together, so they're sharing electrons. But the thing is that the shared electrons are not uniformly distributed throughout the molecule. So what we're going to do is use a process of assigning oxidation states in order to figure out if in fact anybody is getting a little more positive or getting more negative. Now, to assign oxidation states, we have a set of guidelines that we follow. And we're going to go through several examples today so you can see how these guidelines are applied. And as you do more and more examples on your own, you'll just get really familiar with the process. First guideline is that you have an element, if you have an element in the reaction, and the element is in its naturally occurring state, solid, liquid, gas, then you assign an oxidation state of 0 to those atoms. Here's sulfur as a solid. That is how sulfur occurs in nature. So I'm going to put a 0 for the oxidation state of those sulfur atoms. Likewise, I have another element, oxygen. And in this reaction, it's in its gas state, and that is how oxygen occurs in nature. So I'm going to say that these oxygen atoms also have an oxidation state of 0. All right, the next guideline that I will pay attention to is this one. If in a compound you have oxygen atoms, those oxygen atoms are assigned an oxidation state of -2. Here in my compound, I have oxygen atoms. I'm going to assign oxidation state of -2. Do you see how I write the assigned oxidation state straight up above the atoms symbol like a little top hat? All right, my third guideline to consider is that when you have a compound, you have to make sure, as you're assigning states, that the sum of all the oxidation states in that compound adds up to 0. All right, so my oxygens have -2 state. Notice there's 2 of them. So I really have -2, -2, and therefore the sulfur in this compound must have an oxidation state of +4. That ensures that the sum of everybody in this compound is 0. Now, as you look at the reaction in its totality, are you finding anybody that has gotten more positive? Is oxidation going on? The sulfur atoms started in the 0 state and they ended up in the +4 state, that's oxidation. And so we say that those sulfurs were oxidized. And if you have somebody getting oxidized, then there must also be someone getting reduced. Notice that these oxygen atoms are assigned oxidation state 0, but on the product side, -2. So the oxygens got more negative, and that means they were reduced. Okay, let's keep practicing. Here's another example. So we have this time an aqueous solution of the ionic compound iron 3 chloride. I call it iron 3 because I can tell from this formula, you know how iron can be either 2+ or 3+? Well, in this compound, I have 3+. And hydrogen gas reacting together to produce the ionic compound iron 2 chloride. These irons are 2+ cations and hydrochloric acid. All right, so let's go about assigning oxidation states. Looking at my guidelines, elements have oxidation state of 0. So here's the element hydrogen. I'm going to assign oxidation state of 0. All right, here's a new guideline to consider. In a compound, hydrogen atoms will always have the oxidation state +1. So not here, this is hydrogen, the element, but over here with hydrogen in the compound, I'm going to assign oxidation state of +1. Okay, I have yet another guideline. Ions, whether they're in a solution freely swimming around or they're within an ionic compound, the oxidation state of those ions is simply going to be the same as their charge. So let's go back to this ionic compound made of iron 3+ cations. The 3+ cations have oxidation state of +3. And the anion is chloride. The charge on chloride anions is 1-, so the oxidation state is -1. Over here on the product side, the ionic compound is iron 2 chloride. It's the iron 2+ cations forming a compound. The 2+ cations would have an oxidation state of +2. See how simple that is? And my chloride anions are still 1- for their charge, so the oxidation state is -1. And then lastly, this hydrochloric acid is not an ionic compound. It's molecular, but remember that strong acids in aqueous solution ionize. They turn into ions. So the chlorine atoms are going to become chloride anions with a 1- charge for oxidation state, of -1. All right, now that I have assigned oxidation states, then I have to go about the business of seeing if there's any oxidation going on. Is anybody getting more positive? Okay, well, I have hydrogen on the reactant side in the 0 state becoming a +1 oxidation state. So we're going to say that the hydrogens were oxidized. And that must mean that somebody's getting more negative, somebody's getting reduced. And it's these iron 3+ cations, which have a +3 oxidation state. And on the product side, they have a +2 oxidation state. So even though they're both still positive, they are getting more negative, getting less positive, getting closer to being negative. So even though it is the irons that are getting reduced, it's very common to say that whole compound is reduced. Iron 3 chloride is reduced and the hydrogen gas is oxidized. Okay, let's keep going. Again, just lots of examples is the best way to approach this. Here's a net ionic equation. It's not balanced, and that's okay. So we have the permanganate polyatomic ion in solution and the iodide ion in solution. And on the product side, we're going to have the manganese cation and iodine, the element. Okay, so my first rule in assigning oxidation states is to look for any elements. Now, this iodine, I2, is a diatomic element, and it occurs naturally as a solid. I'm going to assign the oxidation state of 0. Be careful, this iodide over here is not how iodine, the element, exists in nature. Okay, iodine, the element, is diatomic and it's a solid. This, however, is an example of an ion swimming around in solution. Its charge is 1-, and therefore its oxidation state is -1. And here's another ion swimming around in solution. It's the manganese 2+ cation. Its oxidation state is the same as its charge, -2. Let's go over here and look at the polyatomic ion permanganate. Okay, remember that oxygens in a compound and also in polyatomic ions, oxygens are always assigned -2 oxidation state. All right, so that leaves me with the job of figuring out what's the oxidation state of this permanganate. I have yet another guideline that says in a polyatomic ion, the sum of all the oxidation states is the same as the charge. So I'm going to do a little algebra equation here. Manganese has some oxidation state that I don't know. I'm going to call it X. Then I have 4 oxygens, which are all -2. And the sum of all of those is equal to, not 0, as we would with a compound, but the sum's going to equal up to -1 because that's the charge on this poly. So I have X plus 4 times -2 equals -1. X minus 8 equals -1. Add 8 to both sides, and I have X equals +7. So that little bit of algebra finagling there helped me figure out that the oxidation state of manganese in this poly is +7. All right, now is anybody getting more positive? Is oxidation happening here? Iodines are going from the -1 state to the 0 state. That's getting more positive. So we're going to say those iodides are oxidized. The manganese in permanganate is +7 as a reactant. And oh, dadgummit, I goofed here. Did you guys catch that? That should have been a +2. So the manganese are going from the +7 state to the +2 state. Those are both positive cation values, but +7 is getting more negative as it becomes +2. So we say those manganese are being reduced, or we can say the permanganate polyatomic ion is getting reduced. All right, last one I want us to look at is this balanced equation. So let's take a look at our rules. I don't have any single elements here. I do, however, have some compounds that have oxygen. Remember that oxygen in a compound is assigned -2. Okay, now I also have the guideline that tells me if you have ionic compounds, the oxidation states of any ions in the compound is the same as the charge. In this metal, non-metal, ionic compound, I know potassiums are 1+. That means that the oxidation state of the potassiums is +1. Over here, ionic compound, metal and non-metal. Okay, chloride anions from my periodic table are 1 minus charge. So the oxidation state is -1. Chromiums can be 2 plus or 3 plus, but in this compound, I can work backwards and realize I have the 3 plus chromium cation, and so the oxidation state is +3. Over here, ionic compound, metal and non-metal. I know that oxygen anions are 2 minus, and from these subscripts, I can work backwards and say, oh, I've got the 3 plus cation of chromium here, so the oxidation state is +3. My last ionic compound, potassium chloride, ionic compound, metal and non-metal. The charge on the anion is 1 minus, the oxidation state is -1. The charge on the cation is 1 plus, the oxidation state is +1. Okay, assigning oxidation states can be a bit of a labor, but you will get pretty fast at it. Does anybody here get more positive, and does anybody get more negative? Potassium, +1, +1. Oxygen, -2, -2. Chromium, +3, +3. Chloride, -1, -1. Oxidation and reduction are not happening here. This reaction is not a redox reaction. So one of the challenges you'll be asked to do is assign oxidation states and then make the call. Is it redox or not? If it's not, you're done. If it is redox, then of course you have to point out who's being oxidized and who's being reduced. All right, so here, guys, is the summary of all the rules I've just given you. You can pause the video to copy those down. And also I want you to copy this final example and try it on your own, following these guidelines. So go ahead now and pause the video, assign oxidation states, and then if it is redox, determine who is oxidized and who's reduced. Then turn the video back on and we'll check. Okay, pause video. Okay, we're back. So very quickly, you would have assigned oxidation states like this, checking your answers. All of these assignments come from these guidelines. So after you've assigned oxidation states, we're looking for who is getting more positive, and it's the sulfur in sulfite that goes from the +4 state to the +6. So we say sulfite is being oxidized, and that means somebody must be getting reduced. And you see that the chromiums in dichromate are going from +6 to +3. They're getting more negative. So we say dichromate is being reduced. Okay, so that was a lot, but again, you just need lots of practice assigning oxidation states, and you will get faster at it. I know it maybe doesn't feel that way right now. Okay, hope that helped, guys.